Sorry guys, last time there was an internet issue. I think I'm audible. Um,
So the sense amplifier,
yeah, and desktop
what
audio is
does the
also
sense
coming.
amplifier do? It will amplify the
I think I
difference
should
between bitline and bitline
not
bar
check it
to full
again and
VDD and
again.
ground. Is it not?
Yes, sir.
So the bitline would go to full VDD.
So my doubt is, mm, ah, let's say there is 0 volt at this internal node, and somehow it got some delta V voltage greater than 0 volts. So it is some tell V right now. It's because of some leakage current and stuff like that. So now when I try to read data from the internal node, I make this PM node as VDD by 2. So this is connected to SenseAmp and this is VDD by 2. So it will uh, observe the small differential voltage between these two ones, and it will amplify and gives us the output as 0 or 1. So my question is, uh, during this amplification, right, we usually do this. Let me write down the entire circuit. We have a PMOS, and this is a latch. We can use this as a differential amplifier where its inputs, if the inputs have small differential voltage, it can amplify that. This sense enable. And there is an access gate here as well. This is also sense enable. So when I turn this word line on, I'll turn the sense enable as well. I mean, for SRAMs, after turning this word line on, since it is a positive feedback, it's not really an issue because we'll continuously make this node to let's say 0 and this node to 1. So it's continuously uh, kind of, let's say this inverter connecting this node to ground and this inverter connecting this node to VDD. It's a positive feedback. It doesn't, like 0 volt doesn't get corrected and get some delta V in it, and 1 volt like VDD doesn't go down much such that it doesn't appear as a VDD. It's not like that. It's a positive feedback. So continuously these inverters feed back their output, and thus it either connected to VDD or ground always. But in case of a capacitor, this doesn't have any power source. It is just grounded, and the other terminal depends on the bit line and word line access. So if I turn this on, there is VDD by 2 here, VDD by 2 here, and that VDD by 2 tries to charge this up, this capacitor, and this delta V again increases by some delta V dash. So delta V dash depends on the how much time I turn this WL on, right? So I think uh, what I think is by the time WL turns on, this sense enable must turn on, or even maybe or even before, because the critical thing is this one, this capacitor charging up, it's gaining some voltage, it shouldn't be, right? So this WL access, WL turning on the WL time window should be small, and in that time window this node must get this bitline voltage. This bitline voltage is affected by this internal capacitor voltage, right? So actually we pre-charge this to VDD by 2, but due to this internal node capacitor, this VDD by 2 drops by some amount, and that amount of voltage depends on the how much time we turn this WL on. So it should be small, right? So we'll get some drop in bitline voltage, and that will be reflected here. If that has to be happen, then sense enable has to be pin has to be 0. Anyway that is 0, I guess. Yeah, this is always on actually. Only uh, when the signal passes through row decoder and cell replica and then hits the sense amp enable, it gets 1. So then only this NMOS will turn on and these PMOS access gates will turn off. So there is no issue. So when we design self-timing, we should design this WL as a pulse, I guess. It should be a pulse because this capacitor discharges, right? Or else if it is 0, right, it will charge up and corrupts. Okay. So this is my doubt actually. And it's a same case for when the internal node is 1 volt.
If that was what was required, or it will go to full ground if that was what was required. As bit line goes to ground,
So Sar is telling about refreshing. So here we observe that amount of time that we turn on this WL will definitely affect the internal node capacitor, right? Internal node capacitor voltage. It will change. So let's say initially I have 0 volts, and due to some leakage I got plus delta V, and due to some access of bit line through word line access transistor I got some more voltage. So thus it reaches some finite delta V, which is not acceptable. So at this time, this is some threshold voltage, okay? It shouldn't cross this voltage. So now we have attained that. Now we need to refresh this before it even goes to like very close to VDD. Okay, VDD is something that is considered as logical high, but we have logic 0. So we need to refresh this. So for refreshing that, we just simply let's say this is the access transistor, cap, C storage, this is the internal node, baud line, bit line, bit line cap. So you will just give this uh, to a sense amp. It will generate an output, this VDD by 2. It will generate an output, and Sa has told us that uh, this SynSam output is given to the bit line. Uh, I didn't get this. Like, this is given to bit line, and bit line, like, let's say internal node has 0 volt. So we perform read operation and it will sense 0. So that 0 is given, somehow given to this bit line, and it will charge this internal node to 0 volt again. If it had gone up by some delta V or del V, I don't know how we connect this in SAMP output to this internal node. If I directly short this, we usually use latches here, so it's not a good thing. I think we may use some uh, what to say, we may use some this gating. Whenever it is enabled, then only we will connect the split line. So this is something that is related to a refresh cycle. So in timing, when there is a refresh period, we will enable this RF signal. Then this output connects to internal. We'll see.
Ground, the internal node will also discharge. Or as it goes to ground, the internal node would charge up. Or it will go to full ground if that was what was required.
Mm-hmm.
As bit line goes to ground, the internal node will also discharge. Or as it goes to ground, the internal node
I'll
would
check
charge up.
my audio once. Audio is a huge issue in my live stream.
Is that clear?
Sir, how we will generate actually VDD by 2, sir? Because really supplies a
We will
VDD
come
one.
to that. So we आगे जम मत करो. जहाँ तक बताया वहाँ तक is it clear?
नहीं सर, और रिफ्रेश में सर जो रीड बोल रहे हैं तो
Hello.
रीड तो सिंपली रीड कर लिया, रिफ्रेश समझ में नहीं आया,
Okay.
रिफ्रेश में हो क्या रहा है?
Refresh is also simply read.
It's not that loud, but
तो
You're
रीड
just
तो
calling it
but
dummy
sir,
read because it is not triggered by the user. It is simply read. Row by row, you read every row. What happens? All the cells get refreshed. All the cells are written back into.
सर it is a power wasting field, sir.
Yes,
yes,
DRAMs
it's a
consume much more
power
power than
consuming.
SRAM, but
And
they are
sir,
much denser. But they are much denser. आगे बोलो.
रिफ्रेश का मतलब क्लियर नहीं हो पा रहा है, कर क्या रहा है? रीड तो ठीक है, रिफ्रेश रीड सेम है आपने बोला, बट क्यों ऐसा हो रहा है?
So, what do you understand by the term refresh when we talk of DRAMs? What do you understand? I'm not saying that your understanding may be correct or not correct. What do
मीन्स
you understand as of now?
रिफ्रेश सुन के मेरे को यही लगता है सर, सम वोल्टेज वी हैव टू रिगेन करना होता है, उस वोल्टेज पे दोबारा चले जाओ, काइंड ऑफ।
So you want to replenish the charge onto the internal node.
ओके सर,
Whether it was a 0 or a 1, you want to bring it back to the original level. Am I right?
या ताकि हमारा डेटा लॉस ना हो।
Taki data loss now.
यस
So during read operation, what happens?
इंटरनल नोड डिस्चार्ज होगा अकॉर्डिंग टू बिट लाइन वोल्टेज।
Internal node would share
Yes.
charge with the bit
या
line.
शेयर
It may
चार्ज,
get charged up or it may remain low.
यस सर।
So what happens?
इधर इंटरनल नोड विल decrease by some voltage delta V, or it will be a very less voltage.
It will either decrease by some voltage or it will increase by some voltage.
Yeah.
है ना? And then you activate the sense amplifier. What happens? Bit
Sense
line goes to
amplifier
0,
This
and
is
as a
actually
consequence,
VDD
even
by 2.
INT goes to 0.
bit line goes to 0, INT. Yes sir, yes sir. Going to 0, yes sir.
So you were reading a 0. When you initially connected the bit line and the internal node also rose to VDD by 2 minus delta
VDD
because
by
of
2
charge
minus
sharing.
delta.
Because of charge sharing.
Yeah. क्योंकि
Now when you
इसमें
activate the sense amplifier, bit line goes to zero and simultaneously INT also goes to zero. So whatever loss of charge had happened, you replenish that charge.
okay, yes sir.
Okay? And that is
So
why it is called refresh. You refresh that charge.
okay, so every read will do this kind of mechanism in system.
So this is how read happens.
Okay sir.
But for refresh, even if a read operation is not triggered by the user, you will do dummy reads. Every row you will access once every 1 millisecond.
And okay, okay, yes, got it.
ठीक है ना? Anything else?
So I
Sir,
have
how
this
does
doubt.
Yes, Malika.
uh, sir, how does increasing the size of the capacitor lead to uh, increase in the dummy read duration?
Interval. Interval.
Like I have seen
Interval.
this
Yeah,
before,
interval.
and
So you tell me, uh, sense
Q
amplifier
equal
has a
to
offset
CD.
dependent on voltage. That I want
Yes.
the voltage to be
Hmm.
at least this much
Q
there
equal to
so that I
C
can sense a zero or a one.
Yes, sir.
storage.
So and we are saying capacitor will
Let's
leach
say,
charge through M1.
Hmm.
hmm.
So
So leaking is my
voltage
primary
is
issue.
Q is equal to CV.
Mm-hmm.
So
So
let's
Q
say
by C is the
charge
voltage.
leakage. So
If
differentiate, if I
you
differentiate with respect
uh,
to time,
if you increase the
so
charge
I'll
that
get
you can
this.
store on the capacitor,
So it is
Hmm.
indirectly
hmm,
proportional. Okay.
then even if
Inversely proportional.
the same current is leaking,
I leak
the delta V would be
in
lesser
storage.
because
Yes.
the
Mm-hmm.
capacitance is larger.
Leaking.
Mm-hmm.
So sense amp required a
If
particular
this
delta
is
V. Now that delta
constant,
V is lesser
and if
in
I
the same
increase
duration,
the
so you can actually let
capacitance
it
of
discharge for
internal
some more time
storage,
Okay, okay,
and
okay.
then do the
rate
refresh.
of change of internal node
Mm-hmm.
voltage will drop.
So that is how a large capacitor helps in increasing the interval between two refresh cycles.
So if this
Okay,
drop
sir.
is reduced, I can
ठीक है ना?
Mm-hmm.
kind of
Anything else?
increase the
So I understood why we are
time
refreshing,
interval
but
between
can
refresh
you please
cycles.
explain how
This is
we are
refresh
refreshing
cycle
the
1,
internal node?
this is
We
refresh
simply read.
cycle 2.
We simply read every row.
If capacitor
Okay.
capacitance
So
is
when you read a
high,
row, what happens? अभी हमने बात
let's say
करी.
low,
So charging or
uh,
discharging
Sense
if
amplifier
this
will
is low,
fully charge or fully discharge the internal
this is
node.
high rate,
So
yes.
any loss of charge
thus
which could have happened
refresh
because of
cycle's
leakage is
time
taken care
window
of.
Okay.
is reduced. That in the sense
Okay.
you have to refresh it
ठीक है ना?
again
सर
and
जस्ट
again
फॉर
in
क्लैरिफिकेशन जो नोड है सर
with
उसका
a
स्विंग अपन 0 से VDD
higher
लगाते हैं.
frequency when the
Okay, sir.
capacitance is
आप
low.
बताओ. Good question. Very good question.
क्योंकि सर
What do we
अगर
have there? Bitline को int node से क्या चीज connect कर रही है? Is it a transmission gate or a NMOS?
Okay, we don't get internal node voltage complete VDD because it is NMOS. NMOS can drive ground strongly. So VDD won't be reaching here. It could reach up to max up to VDD minus VT. So we need to overdrive this. So like I have even analyzed this that this is WL. Usually WL we assume it is charged to VDD, and this bit line uh, uh, let's say it is a write operation, right? Sense amp will, let's say refresh cycle, sense amplifier will make BL as VDD, and we have internal cap. So in an NMOS we have gate voltage VDD and this node voltage as VDD, and here we have capacitor, and this is actually grounded. This is PMOS. Okay, correct. This is actually grounded. So VDD, and let's say this is 0 volt initial. So there is current flowing because this is VDD and most turns on. uh, how it turns on is this is drain because higher voltage, and this is 0 volts, higher potential, this is lower potential. So there is a current flow until it reaches VDD minus VTN. There is a current flow. When it reaches VDD minus VT, the voltage between gate and the internal node, if you see VDD minus VTN, so it is VTN, right? VGS is equal to VTN. So VGS actually has to be greater than VTN, right? So it is at the critical point now. If at all, if you uh, increase this internal voltage by even some fraction, this relation, this NMOS will turn off. So it won't reach full VDD, it reaches only up to VDD minus VTN. So for this, we can do something that instead of having word line at VDD, we will add some VTN to it. So VDD plus VTN. Here I have VDD plus VTN. Now I have 0. Okay. Now I have 0. No, sorry. How 0 comes? Now I have VTN. Okay, 2 VTN. So 2 VTN is good. If I have VTN, then that's a problem. So now I have a even more chance to increase by VTN. I can increase this internal node by VTN as well. I can add VTN. So if I add VTN to this, I'll end up having VDD. If it's not clear, then say this again. VGS equal to VDD plus VTN minus just source. Source is at VDD minus VTN. So you'll get 2 VTN. There is no problem in that. Let's say internal node goes to VDD. Okay, this is gate, this is source. Now VTN. So if you increase the internal node furthermore, NMOS will turn. But by the way, I have attained internal voltage VDD. That's my goal. So you are increasing the overdrive.
So what is happening here? What would be the,
Sir,
can I transfer a VDD to int node like this?
No sir.
गेट इट सर मतलब सर अगर बिट लाइन को VDD by 2 पे ले लिए और रीड ऑपरेशन सर अगर कर रहे हैं तो 0 इंट पे अगर है तो
Fresh
चार्ज हो जाएगा समथिंग
will
नॉट क्लियर
internal
रेंज क्या हो रहा है वोल्टेज
gets
No, no, if you just try to work it out, what did we say? That I have my bit line at VDD by 2. Let's go to the read wala slide again. I had my bit line at VDD by 2. When the internal node got connected, I discharged a bit and then sense amplifier ensured bit line went to 0, and as bit line went to 0, because this is on, this also goes to 0. This is simple.
यस सर
Now, if int node stored 1, what would happen? Bit line would rise.
yes.
Then
यस
once the sense amplifier turns on, it will take it to 1. Now this 1 on the bit line needs to transfer to int node. How would you do it?
WL हाई रहेगा.
WL हाई रहेगा, वर्ड लाइन हाई है, लेकिन ये तो NMOS है.
यस सर.
तो NMOS
So
कितने?
there will be a VT drop.
So VDD minus VT जाएगा.
Yes, there will be a VT drop. Now, if you do not want a VT drop, what do you need to do?
So pass gate.
Pass gate? Pass gate तो लगाएगा ना?
If we use transmission gate, then area
How?
will
That you
increase.
anyways are doing, na?
And my
You anyways
major
are charging the
concern
transistors
that
on the bit line.
having a
You are
denser memory
sending charge through
that
M1
will
to
be
INT node.
transmission gate. Sorry, I said pass gate, transmission gate.
Oh, so then it's kind of double the area.
Yes sir.
Can you do something else? Think of assist schemes that we used in SRAMs.
Guys, I have
Can you
seen
do
this
something like that over
video
here?
already.
What did the assist schemes do?
I'm not really that
WL
genius
at
to
VDD plus VTH.
tell
Yes.
this.
So we can overdrive the word line. If we overdrive the word line, what happens?
Sir,
Yes sir. Then VDD
that
will.
VTH drop will be compensated.
Yes.
Yes.
The drop gets compensated. ठीक है? Is the refresh operation clear now? If you take word line to a level which is higher than VDD, I can compensate for the VD drop that could happen because of the pass gate. Therefore, DRAMs would have something, some charge pump that would raise the level of word line to a value which is higher than regular. Therefore, DRAMs would have something, some charge pump that would raise the level of word line to a
Okay.
value which is higher than regular.
We have a charge pump to make this word line greater than VDD. We'll write this here.
Word line.
Charge pump.
Okay. Any questions? Okay. So if this is clear, that is memory, the DRAM cell operation is clear, then we look at in terms of refresh overhead. See, we said that refresh needs to happen at a regular interval. So because leakage goes exponentially with temperature, the refresh rate can actually go very high at high temperatures. Okay? What is happening? That you count through all the row addresses once per refresh interval. And in that duration,
Wait. Count through all row addresses. Okay. Usually CPU selects a specific row, right? During refresh, we'll just count every row. We'll just increment the address using a. If we use counter, right, I will. Okay, how do I count them? To have a counter, I must have a counter, right? Let's see. Digital block counter is more. Okay, for every 3 milliseconds, I need to refresh this entire TM. No right possible. Wait, my question was if I simultaneously okay, in a row only single element, like okay. So what I thought is, let's see, like if I have single Zinzan for a single column, how would it write the data, appropriate data to each and every cell in a column? So actually, only one row selects in a given point of time, right? So one column. No.
Sir,
Yes, sir.
that VTH drop will.
okay. Any questions? Okay. So if this is clear, that is memory, the DRAM cell operation is clear, then temperature, the refresh rate can actually go very high at high temperatures. Okay. What is happening that you count through all the row addresses once per refresh interval, and in that duration the memory cell contents are refreshed. What this means is that in that duration, when you are kind of reading these, doing dummy read on the memory array, in that duration, you cannot do another operation because read is happening. You cannot now do any other read or write on the DRAM. So the DRAM is unavailable during the refresh period. Are you with me? Are you able to see this?
Yes, sir.
Hmm? And this also gives a brief quick calculation of that. Uh, if there is a 8192 cross 8192 array and every excess is 10 nanoseconds, so how much total time is given there?
Mm, 10 seconds. And 10 for 8192 64 MB DRAM memory.
Is lost in refresh. So that overhead is also being calculated.
Ninety 10 power minus 8 divided by 3 milliseconds.
Is that okay? Any questions?
Okay, 10 nanoseconds. Mm-hmm. So 10 nanoseconds is 10 power minus 8 in 8192 3 milliseconds. You can see. I mean, 10 power minus 3 plus this will become 10 power minus 4. This is around 2.7%. Right. How did we calculate this? Okay, simple, but let's say this is your time scale and there is a refresh period here and here as well. This refresh period is 10 nanoseconds and for every 3 milliseconds, right? So for every 3 milliseconds, so this window is 3 milliseconds. So in 3 milliseconds, how much time is given to refreshing cycle? So that is 10 nano. For a single column, why did we multiply 8192? Does it mean that refreshing one row takes 10 nanoseconds or what? Thus we have 8192 rows and it will take 8192 into 10 nanoseconds. And so if let's say there is only one row, then 10 nanoseconds by 3 milliseconds, I'll get some value. 10 power minus 3.33. But I have 8192. So that is the time it takes. It's around 26 something, 26 milliseconds. But this is 3 milliseconds. Wait, am I missing something? No, we did something else. Let me check my calculator. So what sorted is we multiply this by 8.92. Thus we got 2.7%. Okay, read time is 10 nanoseconds. So if I select a single row, it will take 10 nanoseconds to read and refresh back. And if I go to another row, it will take another 10 nanoseconds. So something like that. Or am I wrong? Yeah, that's correct. So thus if I go on refreshing 8192 rows, it will take in 3 millisecond time window, around 2.7% of the time will be given to refresh. That in the sense, in 100 seconds, 2.7 seconds is gone for refreshing.
Sir, what is this 10 nanoseconds, sir, exactly? Read time for
10 nanoseconds
SRAM cell or
is reading the DRAM cell internal node voltage and give that to SynSamp and refresh it back. This entire cycle takes 10
like
nanoseconds.
we need
We're
a
not talking about
like base
SRAMs
for
now, na? We're talking about DRAMs.
no, we need a base for comparison, no, sir, between those both, so that we can say which one is better. So what
Sorry?
is this 10 nanoseconds?
No, no,
We need
what
a
do,
base to compare SRAM and DRAM, right?
no?
So
When I'm storing data in a DRAM, who's talking about SRAMs?
okay, so this is only for DRAM then. Okay, so what is this 10 nanoseconds, sir, exactly?
What do you understand by read time?
I mean, without the refresh, only I'm like only a
Turning on the word line, then bit line voltage changes according to the internal node voltage. Then the sense amplifier will be enabled. It will give out the output. That
only
is
regarding the read time.
again fed back to internal node bit line
No,
via
what
the
is
bit
what
line.
is read time according to you?
So, I mean, so the read operation should be completed and like from the starting from the word line to the end where we
Yeah.
read the capacitor value. So
Yes.
I think that should be the read time.
Yes, exactly. That is what it is.
Okay, so we don't have the refresh time in this
Is refresh
included
time
in that.
different from read time? What did we just say? Refresh
Okay.
is equal to dummy read.
Yes, yes, sir. But yes, sir. Sorry.
No,
Yes, sir.
read
But
time.
Oh, okay. Okay, okay. Now, like initially, I got a doubt, right? What did I say? Yeah, I told you about like when I try to read DRAM internal node voltage. In a way, I'm just changing its internal voltage na, by some amount. So that is a loss. I have a leakage loss when the WL is off, when there is no access to bit line. Then there is a leakage loss of voltage. Charge will leak, voltage will change, and that affects the refresh cycle frequency. And even while during the read operation, it will affect, right? There will be some time given to charge this sense amp internal nodes, but this output is connected to bit line via some access transistors or something else is connected, and thus this internal node again replenishes. Okay, but somehow this leakage, this del V caused by leakage, is dominating than this read operation replenishment. Hmm. Okay, so why this happens is uh, maybe for a higher higher performance, we do not turn this on for a greater amount of time. If it had been turned on for a greater amount of time, this would have been charged to its respective voltage appropriately, right? If it has a zero, it completely, like a capacitor, it's not a complete zero or a complete VDD. At least it will almost reach 0 volt or almost reach VDD. if I give enough time. If I give enough time here, I do not get uh, that extra time for reading another address data. So यही time consume हो जाता है. I'll consume time here itself. So I need to uh, reduce this time, and I have to switch back to another address. Thus I have higher performance. As there is a leakage, that will be compensated by refresh cycle. This is everything uh, trade-offs.
Time is the refresh time per row.
Yes.
Per row. So you need to see how many rows are we talking about. How many rows are we talking about? 8192 rows in this example. So 8192 times into 10 nanoseconds upon at what interval? It's at 3 milliseconds interval. So 3 into 10 raised to the minus 3 into 10 raised to the 3. And finally we get the the percentage overhead. Fine?
Fine, sir.
Yes, sir.
Okay. So now we look at how this capacitor is designed. See, we are saying that there is one transistor, one capacitor in the DRAM cell. How do we make the capacitor? So let's look at this
Is
thing
it
over
like
here.
a physical capacitor or something, some creative, intriguing design? One second.
Here. Over here, word line is running in the polysilicon. So word line is taken care of. Bit line connects to one edge of the one terminal of the like one either source or drain of the NMOS, and the other side has to have a capacitor. That capacitor could be made by using poly. Make the capacitor. That there is.
Yes, sir.
Okay. So now we look at how this capacitor is designed. See, we are saying that there is one transistor, one capacitor in the DRAM cell. How do we make the capacitor?
NMOS
So let's look at this thing over here. Over here, word line is running in the polysilicon. So word line is taken care of. Bit line connects to one edge of the one terminal of the like one either source or drain of the NMOS, and the other side has to have a capacitor.
Okay.
That capacitor could be made by using poly, having a little dielectric in between, and then again putting some poly.
Wait.
Huh? So how will this look like in a
This is actually ground.
screenshot? Something like this.
Metal line. This looks something like that. We have some symbols in transformers movies. Poly is used for poly is nothing but a conducting layer, right? It is used to connect to. It acts like a metal. It's a polysilicon. So we have a dielectric. Poly storage. Okay. So if this is big in the sense, capacitor metal area is large, so it can accommodate more charges. Capacitance is high, and this is another metal, this polygate, polysilicon gate, and in between we have dielectric. So poly, this is poly 1, okay, poly 3. Poly 1 is this n plus source drain, and source drain, poly metal 1. So maybe this is uh, bit line, and this is our capacitor. Maybe
where uh, different, what do we say, where the polyfin structure has been used so that overall capacitance is higher.
okay. So instead of having this single top layer, we just I'll draw this. I'll replicate that. So here that is something like this, and you have poly here, and then you connect it one plus, and there is a insulating layer. So what Sari is saying is there is a surrounding structure here. I don't know how we do this, but something like this, so that the capacitance increases. This metal area is increasing, right? Electric
Mhm.
field increases.
This represents, the blue one represents the bit line, source drain region.
Mm.
The pink one is the capacitor. The green ones are the
Polygate.
other plate, other side of the capacitor.
Mm.
This is the polygate. Is this clear? Are you able to see this?
So this structure of poly is making them in parallel, so to increase the capacitance.
Yes. In the so you're going vertically, you're adding fins
Yes,
so
yes.
that in the same area you are able to implement a much higher capacitor.
Okay,
Mm.
okay, sir.
Okay? So this is how this could look like in a bigger setting where the capacitor could actually be made. So over here, and the bit line is over here, and the capacitor is now made between uh, somewhere above, far above, metal 4, metal 5 के बीच में you make these capacitors. Is that okay?
Mm-hmm.
Capacitor can
So actually, word line is here, bit line contact is here, and maybe through this we have capacitor here. This one is capacitor plate, stem.
be implemented in two ways. In the previous one, we said it is right there in the poly, so much below metal 1 itself, whereas it can also be implemented by a metal and metal capacitor. Is right there in the poly, so much below metal 1. Capacitor can be implemented in two ways. In the previous one, we said
This is actually something like this. You have this. I don't know how we make this fins and an insulator in between. Hmm.
uh, it is right there in the poly, so much below metal 1 itself, whereas it can also be implemented by a metal and metal capacitor. So MEM capacitor, where the poly, the plug on the source drain actually comes to a much higher voltage level, a much higher metal level, and over there, this dielectric is added.
Okay.
Hmm? So this is called as capacitor over bit.
Mm-hmm.
Then
Yeah, actually, this is very complicated, right? So we have just made that as simplest, another simplest. This is line, and you have this other node going up, making a square shape. Mm, and around that we have gate. Hmm. Other, okay, actually other, correct. This is actually like green color is ground and pink is C internal node. So this is connected to internal. This is ground actually, and you have internal nodes. I think I should know this. And again, you have another n plus region and this capacitor and bit lines and main thing broad line here, gate, and here you will be having some isolation mostly, but actually there is no isolation here. Hmm.
there are other ways to make capacitors. So capacitance over bit we just saw. the fin capacitors were also just
So this is actually called as capacitor over bit. Over bit.
saw.
And that is a stack.
We will just look at tens capacitors. Tens capacitors, what do they involve? They involve us digging a trench into the silicon substrate.
Okay.
And when that is done, uh,
Stack
I deposit a very thin line
capacitor.
of dielectric there, and then I fill this with poly again. So now in the trench capacitor, you do not even need to go up high up and do not need to waste area due to contacts and VRs or anything like that. The trench can be designed right there inside your memory cell, right next to the source drain region. It can be connected like that, just like this. You see the trench is connected to the transistor source drain region.
Okay. N plus silicon and diffusion is blue. Silicon dioxide, polysilicon, polysilicon. Okay, it's kind of, so you basically, white color is PMOS, right? P plus diffusion, P substrate. Can I draw this? Let's draw this. I'll tend to remember if I draw everything. Let me use similar colors. It's hard to find that color actually. Maybe this one, red lighter. So this is actually as although we don't get to see that internal thing. So I have, it's better to remove this. I have diffusion. I have diffusion. I have polysilicon. No, silicon dioxide. Okay. Oh my god, it takes a lot of time to find these colors. Okay, I have polysilicon. Actually, what would really happen is first I'll have this polysilicon at the first place. On that, I try to have this P substrate. This is P substrate. Correct. Yeah, this P substrate. And this is the trench. So again, after this, I go for diffusion. So I have diffused here and here again. These are my diffusion layers, and then I'll implant polysilicon here. So after polysilicon now, these names I just randomly say names, man. This is polysilicon. It should be a metal, and it is connected to ground. And this is P substrate, and these are interest diffusion. And this is SiO2 silicon insulator. So this is my insulator. I need to have metals. So this I'll color metal with some other color rather than there are a lot of conflicts in it. So this is my metal. This is my metal. Metal area is high, then the capacitance is high. So this is my metal, and this is my silicon dioxide insulator, and white color is P substrate, and this light blue is N plus diffusion, and this one finally is polysilicon.
Any questions?
So the trench one is less complex while designing.
Yes.
Okay.
The trench one is actually complex in designing, and you see, this is how the DRC is defined. The aspect ratio. If I keep the trench to be wide, I can go very, very deep.
Yes, sir.
My capacitance can be large. If I do not want to give, but I lose area. If I do not want to give area, then due to the very nature of it being a trench, I go to lesser depth and my capacitor reduces. This is intuitive. When we wanted to use larger capacitance, we were ready to probably give more area also. But it is important to understand that if area is the primary thing, then you can do something more about it by doing away, for example, with the depth. Is that okay?
Hmm.
The area is the main concern over here. Like
Yes.
yes,
You reduce the area, you reduce the area, you therefore end up reducing the depth and the capacitance value,
yes,
the amount of capacitance. So area and capacitance are a direct head-to-head trade-off. Hmm? So what did we look until now? That the capacitor should be big. If the capacitor is big, I can do faster, more robust read. I can
Leakage like drops are less.
reduce
And
refresh requirements.
mm,
Uh, I want to keep a big capacitor, but I
area
want to
loss.
reduce the area penalty.
Mm,
And see, if the capacitor is big, what happens?
charge time increases.
To discharge or charge the capacitor also takes longer. So write time also increases.
Mm,
But we somehow should ensure that write is non-timing critical. How do we do that? We already talked about word line overdrive.
okay.
We talked of it in terms of ensuring that
The
there is
increased gate voltage much higher, then the speed will be high because of the current.
no VT drop at the store node. But in reality, when you do word line overdrive, you also speed things up a bit. So write operation should not be timing critical. Only read
Mm,
operation should be timing critical.
okay.
Hmm? So reduce, if I want to reduce area, then capacitor becomes smaller. Um, However, bitline capacitance either remains same or increases. Hmm? So bit
It if it is big, I'll be having faster, robust read and refresh rate decreases. Area as area has to be minimized. Area loss to be minimized. Yeah. That is appropriate. Area we are losing area. And try to be somehow managed. Mm, by increasing the gate voltage. W.
either remains same or increases. Then capacitor becomes smaller. Um, However, bitline capacitance either remains same or increases. Hmm? So bitline capacitance per bit cell. So the reality is that as the scaling happens, I should use bigger capacitor. As I go to more finer geometries, I need bigger capacitor. But the density requirements of the advanced technology would limit me to use a smaller capacitor. Hmm?
Hmm.
In advanced technologies, trench capacitors therefore are limited because trench capacitors try to reduce area.
Hmm.
Hmm? Try to reduce when you want to reduce the area in the trench capacitors, the capacitance value reduces, but you want to increase the capacitance. So
Hmm.
uh, the metal in metal capacitance or the capacitance over bit is more promising for advanced technologies.
Okay. This one is more promising.
Is that okay?
yes, sir.
Here, if I
Hmm?
go on scaling the
When you
technology, the
use metal in metal capacitor,
trench depth
there are more steps
decreases, right?
involved. More steps
The
involved means
capacitance
more
decreases.
defectivity can come into.
But I need more capacitance to have more robust writing or reading the capacitor internal nodes, especially writing.
Picture there can be yield loss.
Faster, more focused read. These can be managed by using overdrive.
Uh, Otherwise, there are, any decision that we make also.
The challenge is scaling down techniques will uh, kind of reduces the what do we say that area of pipe. मतलब distance between two trenches will decrease. So let me show you the picture. Try to get how much clarity. So if I scale down, I'll come to these scenarios where the depth decreases. Thus capacitance decreases.
Hmm? In advanced technologies, trench capacitors therefore are limited because trench capacitors try to reduce area.
Hmm.
Hmm? Try to reduce when you want to reduce the area in the trench capacitors, the capacitance value reduces, but you want to increase the capacitance. So uh, the metal in metal capacitance or the capacitance over bit is more promising for advanced technologies. Is that okay?
Hmm.
Yes, sir.
Hmm?
My solution is
When you use metal in metal capacitor, there are more steps involved. More steps involved means more defectivity can come into picture. There can be yield loss. Uh, Otherwise, there are, any decision that we make also has an impact on speed on performance improvement, not just area. So all these three things have to be kept in mind when you are deciding which kind of technology to go for. Now, if you're going to join any circuit design company, then it doesn't make a difference because this thing will be decided for you by the company itself. But if you're going to join a company which does
startup.
not have its own fab and does not have its own capacitance creation process, then you have a choice whether you want to go to TSMC or Global Foundries or ST or someone to choose the technology. And it is for that this discussion is relevant for you. Okay. So until now, what we have seen is that DRAM cell is based on capacitor storage, which is non-regenerative in nature. It has very high density to boast of, gigabits per centimeter square, and there is therefore for imaging processors, graphics processors, or multimedia processors, there is a huge on-chip DRAM also that we are talking about. However, there is a challenge in scaling the DRAM capacitors, and uh, the parasitics become more and more important as we go to advanced technologies. So speed takes a hit, especially in the morning hours. The speed takes a hit, huh? And okay, for DRAM you definitely need periodic refresh.
Hmm.
Is it clear till here?
Could you once again tell why the aid loss was coming in the picture in last slide?
Why the
So about the aid loss.
Yeah. So uh, the more the number of fabrication steps involved,
Okay.
hmm, the more the probability that there will be some misalignment or some extra defectivity that will come into picture.
Mm-hmm.
Since the stem of the DRAM capacitor, the MIM capacitor, needs to be built across multiple process steps, multiple layers. Anywhere, if there is a misalignment, there could be a loss in yield because of some resistance or something that comes into picture. Is it clear?
Yes, sir. Thank you, sir.
Right?
Yes. So this appears to be the same as a SRAM array. Am I right? You have multiple cells, rows, columns, then column selectors, row decoders, everything. This appears to be the same as a regular SRAM array, except there is one difference.
So decoder, bitline data line, each intersection. Okay. Okay. Broad rows, select metals.
That it is always a square. The number of rows is equal to number of columns in a DRAM.
Why?
Hmm? Why do you think this is required? Or why do you think this is done?
Why it should be a square? What DRAM consists is capacitor. Let's say we are using trench or COB. Capacitor over bit or trench wala. So I'm using trench. You have trench and use. I think internal circuitry like doesn't affect at abstract level. Data goes to these things. Mm, maybe. Mm, let me create another page. Logical organization. Maybe in a SRAM cell, we do not have any issue of discharging of the internal storage element. What I mean is, if let's say if it is SRAM, then there is this positive feedback, and the data that is stored in the cell do not get corrupted. It stays there. But when it comes to DRAM, you have a capacitor. You have a leakage issue. You have some this when bitline word line selects uh, word line selects, right? Then there is even more leakage. Let me put it this way: if you have these many columns and rows, and each cell has its access and cap, access and cap. So if I connect this to this row, and if I want to access, let's say this one, so I'll select this, like select in the sense it's I'm writing data. So I'll make this VDD, and this word line has been uh, set to VDD plus VTN. So all these cells will turn on as transistors, and let's say these bit lines are 0 volts, except this one, this is VDD, and let's say there is 0 volt, 0 volt here, and let's say here we have one logic one VDD. Then there will be some discharge, right? Then there will be some discharge. Then it's crucial to make only this like specifically only this cell has to be turned on. This word line has to be turned on. Then I need to have this column and this row to be ungated or something sort of that. Then give this to word line. I think this is an issue. I think so. Then why this patient? Why only square? Is this a reason? I have, let's say, 4 rows and 2 columns. How many cells I can have? This is a cell. This is another cell. So I have 8 cells. These are connected in this way. No issue. So this is not the reason. Like, this is not the issue. Pi square. Pi square. Pi square. Mm.
तुक्का मारो.
To have same cap on word line and bit line.
I did not say that the width of the cell is same as the height of the memory cell. I just said number of rows is equal to number of columns.
Mm. Why? Why?
I also did not say that the drain capacitance is equal to the gate capacitance. I just said rows is equal to number of columns.
एड्रेस डिकोडिंग बिट कम यूज हो माइट बी.
सर दोबारा से बोलो.
एड्रेस डिकोडिंग बिट कम यूज हो माइट बी, मतलब कि हम एक ही लेकिन
So actually you're very, very close. So what happens is, uh, let us say we had a 4 megabit DRAM. So you have 2K cross 2K array, and so 4 megabit के लिए कोई एक bit access करने के लिए you would otherwise need 22 bits.
Yes, for 1 megabit I need 20 lines, and for 2 lines 22.
22 address bits. That is a huge address bus. Hello? So there is a huge, very big address bus, 22-bit address bus that we are talking about. able to give that kind of bandwidth, that many number of pins, is not possible when you have off-chip DRAMs. Or
Okay, when I want to uh, go off the chip uh, outside the CPU, I need to have 22 address lines to connect to DRAM. So sir is saying that it's not feasible to have these many address lines connected to the DRAM.
you do not want possible when you have off-chip DRAMs,
Hmm.
or you do not want to route too many signals. So
Yes.
DRAMs therefore say that okay, we will organize our data such that 11 bits are used to decode the
Okay. 11 bits are used to decode the 4 megabit. Let's say I have mm, I have 16 cells. I need 2 lines here and 2 lines here. Correct? 2 lines. Lines. There is some decoding circuit. 2 lines. Decoding circuit. 2 lines. So let's say this is A1, A0, A2, A3. So with A3, A2, A1, A0, I will have 16 different views. So if I use only 2 address lines, that is only, let's see, because 0, 0, this is also 0. We'll get this one, 0, 1, 1. Then only 8 are possible, right? Where's this one?
rows, and 11 bits are used to decode the address, the columns. What we will do is we will first send 11 bits of row address.
Okay. To reduce the routing effort, I have this decoder and I have this column decoder. So I'll get the address lines, 11 address lines. Let's say in our example, 2 address lines, and this will be given to a buffer. So I'll store 2 lines of information first and give that to, let's say, column decoder. And for some time later, some small t time, I'll give these two lines itself to this row decoder. In this way, instead of having 4 lines, I ended up having only 2 lines. But there is this area penalty of having a buffer. Then how do I manage to switch between these two lines? Like when would this accept and when would this accept? There has to be some logic in it.
Then we will send 11 bits of column address. And
Hello. Bye.